everyone, and welcome back to Teach Astronomy. My name is Victoria, but you can call me Vicky, and I am here today for some book stream. So we are getting to the very end, almost, of Dreams of Other Worlds. We've been reading it for a couple months now. It's a long book. So if you haven't been here, essentially this book is all about the story of unmanned space exploration. It's written by Professor Chris Impey and Professor Holly Henry. Every chapter is about a different unmanned space mission. This chapter is about WMAP, and this one is actually the last chapter before the conclusion chapter, which covers New Horizons and some other stuff. So, yeah, I think we're just going to jump into it and learn a little bit about WMAP. So, WMAP, Mapping the Infant Universe. Awareness of the size and age of the universe is hard-won knowledge that has taxed scientists for the past 2,500 years. To ancient cultures, the sky was a proximate canopy that circled overhead, and there was no sense of the vast distance to the stars, let alone the idea that something might lie beyond those pinpoints of light. The ancient Greeks were the first civilization to spawn a class of philosopher-scientists who applied logic and mathematics to their observations of the sky. Cosmology had its root in the Greek idea of cosmos, or an orderly and harmonious system. In the Greek view, the antithetical concept of chaos referred to the initial state of the universe, which was darkness or an abyss. Thus, order emerged from disorder when the universe was born. Pythagoras is believed to be the first to use the term cosmos, and the first to say that the universe was based on mathematics and numbers, although in truth, so little is known about Pythagoras and his followers that direct attribution of those ideas is impossible. Pythagoras is also credited with harmony of the spheres, a semi-mystical, semi-mathematical idea that simple numerical relationship or harmonics were manifested by celestial bodies, with the overall result having commonality with music. Pythagoreans didn't think the music of the spheres was literally audible. Aristotle's geocentric cosmology dominated Western society, maybe? Western thought. I thought it said throughout next, and I was confused. Anyway, Aristotle's geocentric cosmology dominated Western thought for nearly 2 millennia, but Aristarchus developed a heliocentric cosmology that implied large distances to the stars, so as not to observe a parallax shift from one season to another. Mapping the stars in the third dimension didn't become possible until parallax was measured in the 19th century, giving William Herschel an inkling of the extent of the system of stars that we inhabit. Twin foundational discoveries by Edwin Hubble early in the 20th century, the distances to the nebulae, or galaxies, and the universal recession velocities of galaxies, set the stage for modern cosmology. By the mid-20th century, the universe was known to be billions of years old and billions of light years in extent. Good morning, good morning. Ox Bowman, Student McLeod, welcome. Hope you folks are having a good day. Sorry it took me a minute to get started. I forgot I needed to take pictures of the pictures in the book, so I had to take those and send them to myself. Although all of them in this chapter are just graphs, so I might have to be looking up some pretty stuff to look at, because, well, graphs, I guess, are fun. I like pretty things, too. All right. A beginning for the universe. It was only in the most recent seconds of human existence, comparatively speaking, that the universe began to take shape in the human imagination. For the vast majority of the 200,000 years since the emergence of Homo sapiens, the reaches of the depths of space were unfathomable. In just the last 100 years, humans began to discover the universe and develop a basic understanding of its mass and age. One key to unfolding our current view was detection and mapping of the cosmic microwave background, the remnant light and heat of the Big Bang. The temperature of the vacuum of space is 2.725 Kelvin, a trace above absolute cold, exactly what the universe should have cooled to if it had expanded to its current size from a hot and dense initial state 13.8 billion years ago. NASA's COBE and WMAP spacecraft have mapped this signature of the moment when the abyss of space and everything in it came to being. Prior to and throughout the first third of the 20th century, most people, even most astronomers, simply assumed that the universe always existed. Science historian Helge Krauss comments, quote, "The notion of a universe of finite age was rarely considered and never seriously advocated," end quote. Astronomers knew very little about the depths of space before the 100-inch telescope at Mount Wilson Observatory near Pasadena became operational. At that time, they intensely debated whether the Milky Way comprised the entire universe, or whether the nebulae might lie farther beyond our galaxy. On an October night in 1923, American astronomer Edwin Hubble, working with the 100-inch, then the largest telescope in the world, observed a variable star in M31, the Andromeda Nebula, which ultimately confirmed that it was millions of light years beyond the Milky Way. The announcement of Hubble's result in 1925 radically altered the scientific and public understanding of our place in space. Just a few years later, in 1929, Hubble and his assistant Milton Humason again rocked the world by reporting that remote galaxies were racing away from the Milky Way at 700 miles per second or faster. Their observations indicated that the universe was expanding, a seemingly preposterous idea that Albert Einstein himself initially refused to believe. Given that relativity theory recognized space and time as inseparable, the Belgian astronomer and Jesuit priest George, we're going to go with George. George Lemaitre interpreted Hubble and Humason's findings of the runaway galaxies as meaning only one thing. The universe itself was... I'm getting tongue-tied already, oh my goodness. The universe itself was expanding, which in turn suggested that the universe must have been smaller, denser, and hotter in the distant past. Among Lemaitre's many contributions to cosmology, three of his most simple and yet profound ideas were that the universe had a beginning, that both relativity and quantum theory were needed to explain this origin in terms of expanding spacetime, and that Edwin Hubble's receding galaxies were evidence of this cosmic expansion. Lemaitre was the first to suggest that Hubble and Humason's redshifted nebulae indicated the expansion of spacetime itself. In 1931, in the journal Nature, Lemaitre offered a short proposal for what English astronomer Fred Hoyle later derogatorily dubbed the Big Bang. In that article, Lemaitre postulated, quote, "the beginning of the universe in the form of a unique atom, the atomic weight of which is the total mass of the universe," end quote. He theorized inflation of the cosmos from a primeval nebula, or primeval atom, of dense matter. Working from Einstein's theory of general relativity, as well as emerging theory in quantum mechanics of elementary atomic particles, Lemaitre proposed that the universe inflated from a dense, highly compacted soup of subatomic particles that at a moment of quantum instability resulted in the unfolding of space. Quote, "What's remarkable about his Nature letter," writes John Farrell, "is that, apart from discussing the idea of a temporal beginning of the cosmos, it marks the first time that a physicist directly tied the notion of the origin of the cosmos to quantum processes." End quote. Even before the neutron had been discovered, Lemaitre understood that the beginnings of the universe could be explained in part via quantum theory, and argued that, quote, "all the energy of the universe was packed in a few or even in a unique quantum," end quote. By Lemaitre's estimation, space and time, or spacetime, could, quote, "only begin to have a sensible meaning when the original quantum had been divided into a sufficient number of quanta. If this suggestion is correct, the beginning of the universe happened a little before the beginning of space and time," end quote. Lemaitre depicted the early universe as analogous to a conic cup, the bottom of which represents the first instant at the bottom of spacetime, the now which has no yesterday because yesterday there was no space. In 1934, in The Evolution of the Universe, Lemaitre outlined his fireworks theory of evolution, in which the stars and galaxies, having evolved over billions of years, were merely, quote, "ashes and smoke of bright but very rapid fireworks." He described our situated view from Earth, scanning the night skies as we look back towards the primordial past. Quote, "Standing on a well-chilled cinder, we see the slow fading of the suns, and try to recall the vanished brilliance of the origin of the worlds." End quote. Lemaitre additionally intuited that a fossil light would be the signature of the universe's beginning. As James Pebbles, Lyman Page, and Bruce Partridge point out, quote, "One learns from fossils what the world used to be like. The fossil microwave background radiation is no exception." End quote. Lemaitre expected evidence of a fossil radiation from the early stages of the universe could be detected. Thinking in 1945 that cosmic rays were the signatures of this fossil light, Lemaitre supposed that these ultra-penetrating rays would reveal the primeval activity of the cosmos, and were evidence of the super-radioactive age. Indeed, they are a sort of fossil rays which tell us just what happened when the stars first appeared. End quote. Just weeks before his death in 1966, Lemaitre celebrated learning of the discovery of the cosmic microwave background, the fossil light he had anticipated. Throughout his career, he debated with Einstein whether or not his cosmological constant was a repulsive force that, quote, "could be understood as a vacuum energy density," end quote. Cosmologists now regard Einstein's cosmological constant as indicative of the effects of dark energy contributing to the universe's expansion. That's the end of that section. And I have a figure for you. They're not pictures this time, they're just figures. But we will find pictures. So this is, oops, that's not what I wanted to do. I wanted to zoom in. There we go. So this is just a little graph that says, that shows the recession of galaxies that implies the universe is expanding. So as you see, 13.8 billion years ago, 8 billion years ago, everything was obviously really, really close because there was just one atom, and it has, you know, oh, and these are different, so these are the different, what's it called, ideas of, okay, so it says the curves show the past and future expansion of the universe in terms of matter content and dark energy content. So these, it's a slightly similar, or a slightly different graph from the one that's in the book, but I think this is showing how it would be if it was a closed universe, a flat universe, an open universe, and an accelerating. But we know that it's probably an accelerating universe. It is. But these can also be seen as, this is the, is that right? It's a little confusing. Essentially, this is saying that as time goes on in the accelerating universe model, galaxies get farther away. Yeah. And that's because of dark energy and dark matter. Well, just dark energy. It's a little confusing, as I said, because the graph on here is labeled differently than the graph in the book, but they look exactly the same. So, well, you know, we'll figure it out together. All right. I'm gonna move this a little. How was everyone's weekend? My weekend was all right. I was looking outside because it's very gloomy today. We have June gloom right now. Hope the weather by you guys is nice. I was hoping for rain, honestly. There was like a slight sprinkling, but it has eluded us again, as it typically does in the desert. All right. The hot Big Bang. Pivotal roles in science are often taken by outsiders. The father of the Big Bang model was a part-time lecturer at the Catholic University of Leuven, when he published a paper in a journal that was little read outside Belgium. Georges Lemaitre was a Catholic priest who had moved from civil engineering into physics and astronomy. I'm going to keep saying this guy's name, so I'm going to look it up because I don't think I'm saying it right. So let's go on a little adventure. Because I feel bad continually butchering it. Okay, How do you say his name? How to pronounce George Lemaitre? You guys will probably hear this, so you'll get to learn too.
George Lemaitre.
I don't know if you guys heard that. Probably did.
George Lemaitre.
I got it wrong. Lemaitre. Okay. So now we know. George Lemaitre was a Catholic priest who had moved from civil engineering into physics and astronomy. Einstein was initially skeptical, but at a seminar by Lemaitre in Princeton in 1935, he expressed his admiration for the beauty of the theory. The other intellectual parent of the scientific theory of creation was a Russian immigrant called George Gamow. This physicist was elected to the Academy of Sciences of the USSR at the age of 28, the youngest person ever to gain that honor. With his student Ralph Alpher, he showed that the early hot universe could have produced the amount of helium we see, which is too much to have been produced by stars. Gamow jokingly had his colleague Hans Bethe listed on the paper, so it would read Alpher Bethe Gamow, and a pun on the first 3 letters of the Greek alphabet. Bethe had no other role in the paper. In 1948, the same year Gamow and Robert Herman predicted that the afterglow should have cooled down after billions of years, filling the universe with microwave radiation at a temperature of 5 degrees above absolute zero, or 5K. However, nobody pursued the prediction, due to in part a lack of widespread awareness of the theory, and in part to the primitive state of microwave technology at the time. The new theory was given its catchy name by Fred Hoyle in a BBC radio broadcast in 1949. Even though he advocated the rival steady-state theory, which didn't involve a hot and dense early phase for the universe, he claimed the label was descriptive and not pejorative. As Hoyle noted, with typical sardonic wit, the Big Bang was an audacious theory. The entire universe, holding enough matter to yield more than 1 trillion stars and many billions of galaxies, somehow emerged instantaneously and without any precedent from an iota of space-time. Steady-state theory called for the gradual creation of matter in a vacuum of space between the receding galaxies. Although spontaneous creation of matter was ad hoc physics, it seemed like a more modest proposition. For 15 years, the status of the theory remained tentative. The universal recession of galaxies certainly pointed to a time when the universe was smaller, denser, and hotter. The explanation of the fact that the universe is 1/4 helium by mass and 10% by number of atoms was a success, but the difficulty of measuring cosmic abundances of other light elements meant no further progress could be made on testing this idea, called Big Bang nucleosynthesis. Counts of extragalactic radio sources indicated the population was evolving, and argued against the steady-state theory. The missing ingredient was a decisive observation that favored the hot Big Bang. It came by accident in 1964, when 2 engineers working at Bell Labs in Holmdel, New Jersey, detected a microwave signal of equal intensity in every direction in the sky. NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, is the illustrious descendant of this pioneering experiment. And I have another graph for you, very exciting. Here she is. So this graph just says that theorists working with the expanding universe model predicted that the universe should be filled with relic radiation from the Big Bang, diluted and cooled by the expansion to just under 3 Kelvin. NASA's COPE satellite measured the spectrum and shows the radiation had exactly the predicted temperature. The data fit the model so well that the error bars are smaller than the thickness of the curve. So this is the this is that research. So this is the cosmic microwave background radiation, essentially. So yeah, cool. There's not much to say about these graphs. They're kind of simple. Oh, code breakers. Yeah. I heard about that. I should check that out. With the CRISPR gene editing. I heard apparently they fully mapped the human genome or something, like over the weekend. I don't know if they mapped it over the weekend, but oh, units like the vertical one just kill me. I know, look at this. Intensity, 10 to the -4th ergs per centimeter squared. I don't even know what SR stands for. Second centimeter to the -1. I'm like, okay, if you say so. Do I know what that means? Absolutely not. That's why I was like, so this is that. I'm just here to read the stuff, okay? I could not tell you how to reduce that unit in any way. It's wild. All right. Let's see. Cosmic microwave background radiation. Scientific discovery rarely unfolds smoothly or predictably. 8 years before the theoretical prediction of relic radiation, Andrew McKellar measured the spectra of stars and discovered interstellar material that was excited to a temperature of 2.3 Kelvin. He had no explanation for this excitation, which is caused by the radiation from the Big Bang. While Gamau's prediction of a universe bathed in cold microwave radiation sat in the literature, several experimenters had the detection of the radiation within their grasp, but either did not control systematic errors well enough or were not aware of the importance of the observation. Robert Dike at Princeton was, and by 1964, he and his team were hot on the trail of the Big Bang signature. But as they were preparing a radiometer on the roof of the physics building, as they were preparing a radiometer on the roof of the physics building, they got a call from Bell Labs. Quote, "Boys, we've been scooped," was Dick's memorable phrase. The Nobel Prize was awarded in 1978 to Arno Penzias and Robert Wilson of Bell Labs for their discovery. What was the nature of the radiation that Penzias and Wilson detected? To understand this involves rewinding the history of the universe to its very early epochs. The Hubble expansion is a linear relationship between distance and recession velocity. More distant galaxies are moving away from us quicker. Although at first glance this seems to imply that we have a privileged location in the universe, a hypothetical observer in another galaxy would see exactly the same relationship that Hubble saw. In a uniform three-dimensional expansion, I have been taken by a yawn. In a uniform three-dimensional expansion, each observer thinks they are in the center of the universe. Since all cannot be, none are. Nor can we see an edge to the universe, so we can't place ourselves with respect to a boundary. The Copernican principle holds. There's no discernible center to the universe. Reversing the expansion projects to a time when all galaxies were on top of each other, the Big Bang. But a simple backward extrapolation overestimates the age of the universe, because matter tugs on other matter, so the expansion rate has slowed since the earliest epochs. In an expanding universe model, the major observable is redshift, a stretching of the radiation from distant galaxies due to the expansion of spacetime itself. Redshift is simply related to the factor by which the universe has expanded since the radiation was emitted. 1 plus the redshift is the expansion factor. Ironically, the universe is easier to understand in early times. Before structure forms, the universe behaves just like a simple gas, where the temperature and the average density both increase going back toward the Big Bang. Once gas starts to collapse by gravity, the physics is very complex. Stars and galaxies started forming when the universe was about 10 times smaller than it is now, about 13 billion years ago. Extrapolating further backward, there was a time when the universe was much denser than it is now, and hot enough that atoms were ionized. Electrons liberated from atomic nuclei interacted with radiation and stopped the photons from traveling freely. It was as if the universe was shrouded in an impenetrable fog. As the universe expanded and thinned out and cooled, it became transparent, and radiation could travel without interruption. The special epoch is the earliest time we can see into the universe. In a Big Bang model, the background radiation comes from a time when the universe was 1,000 times smaller than it is today, and 1,000 times hotter. infrared photons from 380,000 years after the Big Bang, when the temperature was about 3,000 Kelvin, have been stretched 1,000-fold to become microwave photons in a vast and frigid universe with a temperature a little below 3 Kelvin. The picture of the sky in microwaves is an extraordinary baby picture of the universe. Imagine as an adult that you were shown a picture of yourself a few hours old. Since those waves are from the universe as a whole, they permeate space and they travel in every direction through expanding space. There are trillions of relic photons from the Big Bang in any volume like that of one breath. However, their radiant intensity coming from any direction in space is only 0.00001 watt, or a 10 millionth of a light bulb. If you can find an old-fashioned image tube TV and tune it between stations so you see only static, about 1% of the white specks on the screen are interactions of the dots of phosphor with those microwaves. The Big Bang is all around us. That's the end of that section. We normal people can just say intensity, right? The intensity is that, yes. You've read that some percent of the static once you... Yeah. That's the end of the... Yeah. I guess it's 1%. But yeah, I always thought that was really cool. Just like one of those wild things that, like, you know, you'd never think about. Is 1%, according to this book, at least. Yeah. Yeah, very cool. Polar bear in a snowstorm is actually 1%. 1% the universe. All right. Fingerprints of the Creator. Observations of the cosmic microwave background rapidly improved, and it was soon found that the radiation had a spectrum almost perfectly consistent with one temperature, a type of radiation with what is called a thermal spectrum. This was additional support for its interpretation as relic radiation, because such a smooth spectrum only results from radiation that's in equilibrium with its surroundings. Since in this case the surroundings are the universe itself, thermal radiation is expected. Its temperature is 2.725 Kelvin, and it is the most accurately measured temperature in nature. By the early 1970s, theorists had predicted that the microwave radiation should not be perfectly smooth. That's because a slightly uneven distribution of matter causes very small variations in temperature, with denser regions hotter. The subtle variations in density act as the seeds for later structure formation. Theories of galaxy formation could not generate large lumps of matter without a little lumpiness with which to start. The initial variations are not really like lumps, since they are physically extremely large and extremely shallow. In a purely metaphorical sense, the mighty oak trees that are present-day galaxies grew from the tiny acorns of anisotropy. Anisotropy? The differences in intensity in the background radiation. NASA's Cosmic Background Explorer, COBE, was launched in 1989 to make more precise measurements of the microwave radiation than can be made from the ground or from high-altitude balloons. COBE was cheap by modern standards, about $150 million, and extraordinarily successful. It confirmed the exquisite thermal nature of the spectrum, ruling out the last few remaining potential explanations other than the Big Bang. With only 4 years of data, the satellite was able to detect minute variations from smoothness. The radiation deviated from a constant temperature from one part of the sky to another by 1 part in 100,000. These were the long-sought seeds of structure formation. Commentators and media pundits breathlessly embraced the story when project leader George Smoot talked about having discovered the fingerprints of God. Smoot and his colleague John Mather shared the 2006 Nobel Prize in Physics for their heroic work in advancing cosmology with the detection of these tiny fluctuations. But there's an extraordinary twist to this story. The smoothness of the microwaves and their perfectly thermal spectrum are difficult to explain in the standard Big Bang model because the universe was expanding so quickly early on. At the time the microwaves were released, 2 points in space were receding at nearly 60 times the speed of light. Under these conditions, there's no way disparate parts of the universe could come into equilibrium, so adjacent patches of the sky shouldn't be at exactly the same temperature. A related puzzle is the near flatness of space. General relativity is based on curved spacetime, and it was expected that the vast mass of the universe would give an imprint of curvature. The cosmic background microwaves have traveled across the entire universe, so should reveal if the space they've traveled through is curved. It's not. To explain the smoothness of the radiation and the flatness of space, cosmologists have hypothesized a fantastically early time, only 10 to the negative 35 seconds after the Big Bang, when the entire universe expanded exponentially due to physics involved with the unification of three fundamental forces of nature. This event is called inflation. Inflation modifies the Big Bang theory by positing that all we can see to the limit of vision is our telescopes, called the observable universe, is a small bubble of space-time that inflated to become large, smooth, and flat. The totality of space-time is very much larger, perhaps infinitely larger. Moreover, the variations in radiation that will grow to become galaxies are quantum fluctuations from a tiny fraction of a second after the Big Bang. It's an extraordinary hypothesis. Wilkinson Microwave Anisotropy Probe. WMAP. Enter the Wilkinson Microwave Anisotropy Probe. WMAP was conceived as a way of pushing to a new level of precision and a new set of tests of the Big Bang theory. Most of these tests involved looking at... how do you say it? We gotta do another one where we look it up, because I don't want to get it wrong the rest of the stream. Sorry, guys. It's one of those days. How do we say it? Let's see. Let's find out.
Anisotropy.
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 You always had to practice that word before class started. It's weird because you don't know where to put the emphasis. It's not very clear. Anisotropy. Okay. So, most of those tests involve looking at anisotropies in the radiation, small variations in temperature from one part of the sky to another. The all-sky map of microwave radiation has to have foreground emission from the Milky Way removed before it can be interpreted. There is a temperature gradient across the sky caused by the motion of the solar system relative to the universe as a whole at a speed of about 360 kilometers per second. The microwave sky is 0.00335 Kelvin warmer toward the direction of our motion, and the same amount cooler in the direction opposite to our motion. That small signal is also modeled and subtracted out. What's left is a modeled pattern of very low-level variations. Kobe had enough... Oh, it stuck up on me. Sorry. Kobe had enough sensitivity to detect the variations statistically, but with an angular resolution of 7 degrees, the angle of your outstretched fingers at arm's length, it cannot say much about the detailed structure of the radiation. Kobe was a small satellite that traveled in a 900-kilometer high orbit of the Earth. The instrument that measured temperature variations had 2 horn receivers, pointing in different directions, with the satellite rotating every 70 seconds so they could sweep across the sky. WMAP was a much larger and more sophisticated satellite, even though it was a third the mass of Kobe. It collected microwaves with a pair of 1.5-meter dishes, and its receivers detected the radiation in 5 frequency bands. It rotated every 130 seconds and made a complete map of the sky every 6 months. The satellite was launched in 2001 and sent to a Lagrange point, where the gravity of the Earth and Moon balance, 1.5 million kilometers from Earth, where the contaminating radiation is much lower than in low Earth orbit. As a result, WMAP was 45 times more sensitive than Kobe, and it was able to resolve 35 times smaller regions on the sky, or 2 times smaller than the angle of the full moon in the sky. The large difference is comparable to the gain of the Hubble Space Telescope over a 1-foot diameter telescope on the ground. WMAP operated flawlessly for 10 years. And the exciting results of COBE and WMAP generated the momentum for a third-generation microwave satellite called Planck, named after the Nobel Prize-winning German physicist. Planck is primarily a European mission. Launched by ESA in 2009 to a location at the same Lagrange point as WMAP, it improves on WMAP in both sensitivity and angular resolution. That's the end of that section. Oh, I've just been typing stuff into Google, and then clicking the first result that comes up. The Lemaitre, hopefully I'm getting that right again. That was just like, I typed his name into Google and said pronunciation, and it gave it to me like right in the search results. The other one was just a, like one of those channels on YouTube that does pronunciation stuff. Homogeneity? I think I know how to say that one. I think it's homogeneity, right? Or homogene. Well, now you got me one. Oh, now you make me question it. Okay. I knew that one. I think there was an image, though, since we're talking about WMAP now. And there's no image in the book. I'm going to show you guys an image because I want to. Hope that's okay. That looks incorrect. I guess it's not, though. It looks it looks like it's photoshopped together. It's not. I think this is just a picture of it, but it looks really funny. Oh my god, I forgot this is what it looks like. So this is WMAP. And it really does look like this doesn't look like it's actually a, this is it. But doesn't it look like it's like photoshopped together? It looks very funny. But this is WMAP. It's up, as they said, at the L2 Lagrange point. And it's taken a lot of really important observations of the cosmic microwave background for us. So it's pretty cool. And I will show you that if you haven't seen like the famous image of the background radiation, we will do that later because it like mapped it and it's very cool. But I'll leave you in suspense for now. We will continue. All right. Piper at the Gates of Dawn. Variations in the microwave radiation capture important information about conditions in the early universe. To describe these variations, astronomers like to think about the power spectrum of the variations, or how much of the variation is on a particular angular scale. In this formalism, L is the angular frequency of variations. For example, L equals 2 corresponds to 2 cycles across the sky, or variations over 100 degrees, showing the dipole of the local group motion mentioned earlier. The 7-degree limit of COBE corresponded to L equals 30, and the much better 0.3 degree resolution of WMAP reaches almost to L equals 1,000. Think of L as the number of waves to go all around the sky in a circle, and L squared as the number of tiles needed to cover the sky. Having more tiles means each one covers a smaller area of the sky. The shape of the angular power spectrum is compared to predictions from the Big Bang model. It's fair to think of L as characterizing the harmonics of variation of the radiation. And there's a graph. Let's see the graph. Okay. Boop. So this says a graph showing the amount of temperature variations on the vertical scale versus the angular scale of those variations on the horizontal scale. The quantity L is like a harmonic, so it represents how many waves can fit across the sky. So larger L means smaller feature on the microwave map of the sky. The peak in microwave power on scales of a degree dates from 400,000 years after the Big Bang. I don't know. I'm pretty sure it's definitely partly NASA, but it might be like a multiple agency mission. Let me see. It looks like the operator is listed as NASA. And it's like NASA NRAO. So it looks like it's primarily a NASA mission. But, you know, with NASA missions, they typically share a bunch of their information with everybody. So, yeah. Cool. For reference, on the horizontal axis, the moon or sun subtends an angular diameter of 0.5 degrees. Thank you for that context. Yeah, if you guys want to see that again, here it is. So, this is where the moon or sun is, as Student McLeod explained. Yeah. Cool. All right. The physics of the early universe is esoteric, but we can gain insight by the analogy with sound as long as we don't stretch the analogy to the breaking point. Before 380,000 years, while radiation was still trapped by matter, the electrons and photons acted like a gas, with the photons ricocheting off the electrons like little bullets. As in any gas, density disturbances moved at the speed of sound as a wave, a series of compressions and rarefactions. Compression would heat the gas and rarefaction would cool it, so the sound waves would manifest as a shifting series of temperature fluctuations. When electrons combined with protons to become neutral atoms, the photons from slightly hotter and cooler regions traveled unimpeded through the universe. So the temperature variations that we see now are a frozen record of fluctuations from that time. If there was a piper at the gates of dawn, then who or what was the piper? Inflation is presumed to be the mechanism in the very early universe that rendered space flat and smooth. So it also must have been the source of the initial tiny variations. Those variations from inflation were hugely expanded quantum fluctuations, with the special property that the strengths of disturbances on all different scales were about equal. The disturbances are all produced at once from the very moment of creation, so they make sound waves that are synchronized. The result is sound waves with a series of harmonics or overtones, like the sounds from a flute with holes at regular intervals. Other models from the origin of disturbances tend to be more chaotic or random, so they predict sound waves like those from a flute with holes at irregular or random intervals. Inflation is the music of the spheres dreamed of by Pythagoras. In the flute analogy, the fundamental tone is a wave with its largest amplitude at either end of the tube, and its minimum amplitude in the middle. The overtones are whole number fractions of the fundamental tone, so 1/2 its wavelength, 1/3, 1/4, and so on. In the early universe, however, the waves are oscillating in time as well as space, so the waves originate in the first iota of time at inflation, and they end at the time the universe becomes transparent, about 380,000 years later. The fundamental tone is a wave that has maximum positive displacement, or equivalently maximum temperature, at inflation, and has oscillated to maximum negative displacement, or minimum temperature, at the time of transparency. The overtone oscillate 2, 3, 4, or more times faster, and so cause successively smaller regions of space to reach their maximum amplitude 380,000 years later. Thus, we have all the ingredients to interpret the graph of amount of temperature variation versus angular frequency, L, measured by WMAP. There's one more subtlety. Inflation predicts that all the harmonics should have the same strength, but sound with very short waves dissipates because it's carried by the collisions between particles, and when the wavelength is less than the distance a particle travels before hitting another particle, the wave dissipates. In the air, this is just 10 to the -5 centimeters. But in the empty space of the universe before recombination, photons travel 10,000 light years before colliding. So the high harmonics are reduced or dampened out. After 1,000-fold expansion, those scales are now 10 I have coffee and everything, jeez. So 10 million light years. Thus, we don't expect to see significant structure in the local universe on scales much more than 10 times that size. And the clustering of galaxies is indeed weak on scales that large, chalking up another success for the Big Bang model. The piper at the gates of dawn is playing a strong fundamental note, with faint echoes from the higher harmonics, and a steady descent into high-frequency hiss. And that's the end of that section. Anyone else think it's interesting when the Earth, full moon, and sun just happen to appear to be the same size? Oh no, you're fine. I think it's cool, yeah. It's weird. It's weird those things that line up. And that also, like, I mean, that was a big thing in early astronomy that led to kind of the, like, well, I don't know if it led to it, but it was part of the whole, like, geocentric model thing, right? Because it looked like the moon and the sun were basically at the same distance a lot of the time. And so it took a lot of, research and study to figure out that, oh, actually, the moon does go around us, but the sun does not. And we go around the sun. And that's, it's interesting. Because, back, like, imagine, like, 500,000 years ago and farther beyond, you see these two orbs in the sky, and yes, they do, like, come and go at different times, but they look almost the same size. It's hard to imagine that, like, if they're taking essentially the same path and stuff, that they wouldn't be doing the same thing. So, yeah. It's interesting. How long is this chapter? Oh, not too bad. All right. All right. I almost just threw the book into the monitor. Ox Bowman with the solar eclipses would definitely be different. It's also like a cool special thing that they are so close, like they are, like, they appear to be, like, pretty much the same size. Because if they didn't, we wouldn't have the same solar eclipses that we do now. Because imagine that. It's crazy stuff. But if it was a little different, if, the moon was a little bit smaller in the sky, if the sun was a little bit bigger, then we'd never have, like, a full, the moon would always be a little bit smaller than the sun and stuff. And it's cool. Science is cool. Coincidence is cool. All right. Space music. While astronomers were tuning their high fidelity radio antennas to outer space, electronic artists began turning electromagnetic radiation into music. Penzias and Wilson accidentally discovered the cosmic microwave background in 1965, just as high-fidelity equipment necessary for radio astronomy, as well as synthesizers and electronic instruments suitable for rock music, were being developed. Both fields were poised for an unprecedented exploration of the cosmos. Bell Laboratories was the perfect place for this seemingly unrelated exploration of outer space. Having produced the first high-fidelity phonograph recording in 1925, Bell Labs advanced the technology used in radio astronomy and in generating electronic music. Carl Jansky, while investigating at Bell Labs the reasons for static in long-distance shortwave communications, in 1931 laid the foundations for radio astronomy by detecting naturally occurring radio sources at the center of the Milky Way. A quarter of a century later, Max Matthews, also at Bell Labs, began using a computer to synthesize sounds. Often credited as the father of computer music, Matthews wrote the code for the computer program Music 1, which in later iterations became a widely used programming language for computer-generated music. The lab's simultaneous interest in radio technologies and electronic music is hardly surprising, since from its founding by Alexander Graham Bell, the company that became Bell Labs was dedicated to developing electronic media, such as the phonograph, telephone, radio, and other communication technologies. Music historian Pietro Scaruffi contends that it was not the electric guitar, as one might expect, that would, quote, revolutionize rock music down to the deepest fiber of its nature, end quote, but the emergence of electronic synthesizers and computer programs designated for musical composition. By 1966, Robert Moog had developed the synthesizer, quote, the first instrument that could play more than one voice and even imitate the voices of all other instruments, end quote. Within 4 years, Moog was marketing the Mini Moog, a portable version that allowed for live performance with the synthesizer. And in the decade that followed, high-fidelity or hi-fi technology emerged as turntables, synthesizers, oscillators, and other electronic devices became more widely used precision instruments. Even as Penzias and Wilson at Bell Laboratories were measuring the exact temperature of the cosmic microwave background, avant-garde electronic artists like the German group Tangerine Dream began exploring the new music genres made possible by electronic instruments, keyboards, and synthesizers. The group is credited with launching what was referred to as Komische Musik, cosmic or space music, that later evolved into disco, ambient, techno, trance, and other new age genres. Their album Alpha Centauri from 1971 is purportedly the first electronic rock space album in history. Scaruffi writes, quote, "Oh, Squishton, thank you. Thank you so much for subscribing. Thank you for renewing that subscription for your second month. I really appreciate the support. Thank you." We would only have annular eclipses at best. Yeah, I think so. I believe your thinking is right. It's the timing that intrigues you. The sun and moon did not have the same angular diameter a billion years ago. Wait, really? Oh, because the moon is like kind of slowly moving away from us, sort of thing. Yeah. That's crazy, isn't it? Wild how that stuff works, you know? Anyway, where was I? We're talking about Tangerine Dream. Okay, there we go. Scaruffi writes, quote, "Tangerine Dream's music is the perfect soundtrack for the mythology of the space age. They were contemporaries with the moon landing. The world was caught in a collective dream of the infinite. Tangerine Dream gave that dream a sound." End quote. In 1972, they produced the album Zeit, Time, that included, among other tracks, quote, "Birth of the Liquid Pleiades" and "Nebulous Dawn." Other space-themed selections by the group were titled Sunrise in the Third System, Astral Voyager, and Abyss. Edgar Froese, one of the group's founding musicians, wrote NGC 891 for his solo album Aqua, in reference to the crisp, nearly edge-on galaxy in Andromeda, oriented so that its dust lanes sharply highlight the galaxy's outer spiral arms. English astronomer James Jeans included an image of NGC 891 in his popular astronomy books of the 1930s, and astronomers repeatedly cited this seemingly perfect spiral galaxy to illustrate what the Milky Way would look like from 30 million light-years away. In 1920, Leon Theremin invented an electronic instrument that produced electronic sound by moving one's hands near two antennas that controlled pitch and volume. The theremin's eerie tones often were used to generate sequences meant to evoke space-like themes, and the instrument served as a mainstay in both avant-garde and rock, particularly in the Beach Boys selection, Good Vibrations. Such electronic instruments, along with synthesizers, modulators, and amplifiers, became invaluable to sound designers working in the film industry. Hey, that's what I used to do. And what I still kind of do, I guess. Ben Burtt, for instance, widely known for the synthesized sound worlds of the Star Wars films, actually developed the now easily recognizable laser gun sounds by recording and manipulating the twang of a guy wire from a radio tower after accidentally getting his backpack hooked on one. Okay, it's tangent, but I love talking about sound stuff. some of the things that people do to make these sound effects, like in like Star Wars and like the boom boom of the lightsaber, and all this stuff, like the things people think of, these like Foley sound designers are just so good, and I could talk about it for days. Maybe another time. What were you guys doing? Is it actually coincidence? Woo woo. Play the X-Files music. Oh yeah, I Squishin, I do Monday streams by myself. So Mondays we read this book until the book is over in like 2 weeks, and then we're gonna talk to Chris about it, and then we're gonna play some video games that are space related. But I do Mondays by myself, and then Wednesdays with Michael, and Fridays with Matthew. So YouTubes about Foley are so fun. Oh my gosh. So I took a whole another tangent. I took a whole sound design class in college, and half the class was about, you know, how to do sound and like sound production on set and stuff. But then the other half of the class was like how to do Foley and like how to edit sound and stuff like that. And for one of our projects, we got to take a scene from whatever TV show or movie or whatever that we wanted, and take all the sound out and redo the whole thing. And it was just, I picked a very like high fantasy kind of show. High fantasy. It was an animated show, but it was very like, you know, there's monsters and there's crazy noises and all this stuff, and it's so much fun. It is. I love sound, so I have a podcast because then I get to do more sound design. You love space and electronic synth music, yeah. No coincidence. Anyway, I will get back to rating, but just as the first generation of astronauts was walking in space and on the lunar surface, the related genre of space rock was likewise exploring the cosmos. The genre emerged as an art form during the late 1960s via the British psychedelic movement. The title track to David Bowie's album Space Oddity, which opened with the memorable phrase, "Ground control to Major Tom," shaped much of space rock to come. Pink Floyd's The Dark Side of the Moon, with its closing track Eclipse, is one of the best-selling rock albums in history. American songwriter Gary Wright's Dreamweaver was composed using only keyboards, synthesizers, and drums, and according to Wright, was intended as a kind of fantastical train ride through the cosmos. Innovators like Brian Eno and Steve Roach contributed to space-themed ambient music in their evocative soundscapes. Eno's Apollo, Atmospheres and Soundtracks, the soundtrack for Al Reinhardt's space documentary For All Mankind, was intended to capture the grandeur and strangeness of the Apollo missions. Eno characterizes the soundtrack as evoking the astronauts' somewhat disorienting experience of, quote, looking back to a little blue planet drifting alone in space, looking out into the endless darkness beyond, and finally stepping onto another planet, end quote. He adds that the score was an attempt to extend, quote, the vocabulary of human feeling, just as those missions had expanded the boundaries of our universe, end quote. But the intersection of music and cosmogony? Is that a misspelling, or is cosmogony a word that I've just learned existed? Anyway, the intersection of music and cosmogony, or cosmology, goes back to prehistory, when nomadic people would literally sing the place to recreate and remember a physical landscape in the form of song. Songlines in Australia provide the Aborigines, did I say that right? Aborigines? With unerring navigation over harsh terrain that can extend for thousands of miles. Language may have started as song, and the Aboriginal dream time sings the world into existence. Bringing the concept into the digital age, eclectic singer-songwriter Bjork released an album in 2011 titled Biophilia, where each track is a sensory experience rooted in sound but extending into an iPhone app. With songs ranging from cosmogony to dark matter, I guess cosmogony is a word, Bjork explores inner and outer space with her ethereal, electronic, sonic environments. Let's see another section. There's an awesome space surf rock band called the Gagarin. That sounds fun. That sounds very fun. Now I want to play all these. Now I want to have like a stream where we just like hang out and listen to space music, but like I would so get copyright struck to the gods. Like they would just crucify me if I tried to do that. But it sounds fun. You have a MIDI studio? They are so powerful now. Yeah. It's I've only very, very lightly dabbled in any sort of digital music creation because I used to, because I do a lot of sound design stuff, but I haven't really done the music stuff. I used to play the violin. I kind of play the ukulele, and I've been trying to teach myself guitar and like piano and stuff. But I played around a little bit with some like online programs to make music and stuff. And even just that is so much fun. The things that people can do, it's just amazing. I love it. It's very cool. It's very cool too how like you listen back to music back when like synthesizers were first starting to get popular and stuff, and it was very much used as almost like a gimmick sometimes. A great example is it's not like it's a gimmick as like a problem, but it was just like everyone was like, oh my god, what can we do with this? This is crazy. This is so much fun. But the song Another One Bites the Dust by Queen, which is a great song, but there's like a whole bit that would normally be like a, you know, guitar solo or something that's like a synthesizer solo, and it's wild. It's so much fun. But like you know, stuff like that, where I mean that their whole album that song was off of was very much like, we found a synthesizer, let's do it. But now it's very much like everyone uses synths in their songs, and like, you know, digital samplers and all this like digital stuff. And not only does it give you like a bunch of really cool stuff to do, but it also like lets people who you know, don't have access to an entire orchestra make music, which is really cool, you know. Anyway, that's my rant on music. All right. Celestial harmonies. Oh wait, but first, astrophysicist / queen guitarist Brian May. Yes he does. Oh, I love Brian May. I think you guys have heard the story before, probably. I think Chris has talked about it before, but he kind of went to school with Brian May. They weren't in the same year, but they were like at the same campus at the same time, which is cool. Brian May actually has an album, or no, not an album. I think it was like an EP or something that he put out on vinyl for the New Horizons mission. It was specifically just like space rock guitar kind of things, like vibes for you know, about the New Horizons mission, like for the New Horizons mission. It was like a vinyl exclusive, which is pretty cool. Brian May's really cool. All right, now I'm gonna start the next section for reals though. Celestial harmonies. The correlation between music and exploration of outer space is deeply rooted in the human psyche. The Greek mathematician Pythagoras was purportedly the first to show that musical notes, octaves, chords, and their harmonies were the product of simple mathematical ratios and whole numbers. The Pythagoreans realized that a string attached to an instrument produces a fundamental tone when plucked. Halve the strings and the tone will be an octave higher. Other harmonics or overtones occur at the third, fourth, fifth, seventh, and ninth divisions or intervals of the strings. The Pythagoreans further posited that the universe itself could be understood in terms of this basic mathematics of music, and that the planets, for instance, would be distanced from the sun in intervals similar to the intervals along a string that produce harmonics. By the early 1600s, German astronomer Johannes Kepler was also captivated by Pythagoras' notion of a music of the spheres. He theorized in Harmonices Mundi, the harmony of the world, that musical harmonies could be seen in the motions of planetary bodies. As physicist Amedeo Balbi explains, quote, building on ideas by Pythagoras and Plato, Kepler was trying to give a scientific foundation to the concept of the music of the spheres, the idea according to which each planet moving around the sun, produces a definite sound, end quote. Kepler suggested their orbits would be determined by the mathematics of musical harmonies. Stars, galaxies, even planets naturally produce electromagnetic energy, or low-energy radio emission, as they rotate and move through space. Several planets in our solar system generate strong electromagnetic emissions from their powerful magnetospheres. In the 1970s, the Voyager spacecraft recorded Jupiter's radio emissions. Of course, the human ear cannot detect sound in the empty vacuum of space. However, we can hear the whine of Earth and the eerie sounds of Saturn's radio emissions via satellite recordings, translated by computer programs that render measured frequencies as audible sound. Far more impressive are the acoustic tones of the sun, as we learned in the chapter on SOHO. Astrophysicists are learning a great deal about the interior composition and physics of the sun via helioseismology, by which astronomers track acoustic sound waves that travel through the entire body of the sun. Amazingly, the sun resonates with myriad sound waves that can be measured like musical notes that are directly analogous to fundamental tones and complex harmonic overtones. Turbulence at the top of the sun's convective zone segments the photosphere into granules, thousands of kilometers across, that pulse up and down. These pulses send sound waves careening through the body of the sun and reveal a characteristic acoustic imprint at various internal boundaries, like that between the convective and radiative zones. By recording the acoustic waves traveling through our sun, astrophysicists have a far better understanding of the internal structure of stars, the abundance of helium in our sun revealing its age, the sun's rate of rotation, and how temperatures at the core compare to its million-degree corona. These internal acoustic waves are also associated with storms on the solar surface and are being used to predict future sunspots by detecting disturbances inside the sun. Synesthesia is the experience of one sense being rendered as another, so that you can taste a color or hear visual phenomena. Just as musicians were experimenting with electronic and psychedelic explorations of outer space, astronomers were documenting the sun's acoustic waves and experiencing their own synesthesia. In the case of the tonal resonances generated by the sun's pulsing surface, scientists can hear what they visually detect in this resonance. The first phase of helioseismology, launched from 1960 to 1979, interestingly emerged during the same period as the rise of electronic space music. You heard that many scientists are also musicians. Yeah, I think I think, what's it called? It might be pattern recognition or like a rhythm sort of thing. I think, a lot of scientists in general, I feel like a lot of people in the sciences, in generally STEM careers and stuff, everyone needs to have some sort of creative outlet, right? Because like some of these careers are, there's creativity involved in it to a point, but not in the way that like being a musician for a career or being an artist for a career or being a writer for a career, something like that, is like so very much like creative, and I think having a creative outlet is really cool, and music is a very like accessible kind of outlet. You buy an instrument once and you're kind of good. You'll buy other stuff eventually, but it's not like I feel like some things are a little more intimidating to get into, painting or drawing and stuff like that, where it's like, oh, I feel like I should be good. Whereas music, you kind of are. Music also, you can like, a lot of people get started young. I don't know. It is an interesting correlation though. I like it. You've heard that the sun actually rings like a bell acoustically. Well, sounds cool. I'd like to hear it. All right. Grooves in the cosmic pond. As early as 1937, James Jeans observed that, quote, the tendency of modern physics is to resolve the whole material universe into waves, and nothing but waves. These waves are of two kinds: bottled up waves, which we call matter, and unbottled waves, which we call radiation or light, end quote. WMAP's image of the early universe would seem to confirm Jean's observation that the universe might be understood in terms of waves. Even as sound waves traveling through the sun's plasma reveal information about its structural composition, fluctuations in the plasma that comprise the very early universe reveal critical data about its matter density and structure. Amedeo Balbi, a member of ESA's Planck mission, the successor to WMAP, writes, quote, "The primordial plasma resonated like an enormous bell, and the mechanism which started the vibrations could plausibly only be one, a period of inflation that occurred a tiny fraction of a second after the Big Bang." End quote. Balbi points out that galaxies are clustered through space, and they have a very slight preference for spacings that can be thought of as corresponding to sound waves. These galaxy separations designate grooves or acoustic peaks, as in a wave, and represent gravity and temperature variations on the cosmic microwave background, which evolved into a subtle imprint on the distribution of galaxies. One wave that's clearly detected in the galaxy distribution has a scale of 300 million light-years. Astrophysicist Jean-Pierre Luminet likewise claims that the early universe rang like a musical instrument. He explains that the variations or peaks and troughs we see in the cosmic microwave background reveal details of the universe's mass and density in much the same way acoustic waves reverberating through a drum reveal its structural properties. Quote, "If you sprinkle sand on the surface of a drum," writes Luminet, "and then gently vibrate the drum skin, the grains of sand will assemble into characteristic patterns." Quote, end quote, that reveal data regarding the size and shape of the drum, or the physical nature of the drum skin. Similarly, in analyzing the variation in clusters and superclusters of galaxies, we are gathering details about the matter density of the primeval universe. University of Virginia astronomer Mark Whittle likewise characterizes the variations in the microwave background as similar to the crest and trough of sound waves. Quote, "The waves are actually very long. They're many thousands of light years, and so they correspond to frequencies, pitch, which is very, very low by human standards, roughly 50 octaves below human ears." End quote. Whittle has produced a sound file simulating what the Big Bang would sound like if modulated for the human ear. Describing his recreation of the acoustic peaks in the cosmic microwave background as a quote, "sort of a raw, deep roaring sound," end quote, Whittle is quick to note that there's actually musicality present. He describes WMAP's image of the microwave background as a microscope, quote, "a microscope, a telescope, a time machine, all rolled into one, and stored in it is enough information to kind of diagnose what the character of the universe is today, what its future will be, and what its birth was." Of this extraordinary document, Whittle reminds us that embedded in the image is the primeval nature of the universe, quote, "written by nature in nature's own language," end quote. Kobe and WMAP, and now Planck, have given nature a voice. Amedeo Balbi observes in the music of the Big Bang, quote, "Ripples in the matter density of the early universe had to leave a permanent imprint in the ancient cosmic light, as a seal impressed into wax." Cosmologists theorize that etched into a primordial plasma at the beginning of time were density and heat variations that became the galaxy clusters we observe today. Balbi's metaphor of matter density fluctuations imprinted on the cosmic microwave background as indentations in wax brings to mind an early method of creating phonograph records by etching grooves in wax. Early sound recordings involved engraving data into a wax overlay of a zinc record. Music or voice data were recorded by tracing with a sharp stylus a spiral onto beeswax coating the zinc record. The disc was then treated with chemicals that preserved the grooves where the stylus had removed the wax, after which the phonograph record could be played. As early as 1931, Georges Lemaitre, I can't remember how to say it right. Hold on. I gotta look it up again.
Lemaitre.
That doesn't sound right. Lemaitre. We're going to go with Lemaitre. As early as 1931, George Lemaitre apparently wondered whether information about the universe had been recorded in the primordial quantum, even as information is preserved in the grooves of a phonograph record. Lemaitre observed that, quote, the whole story of the universe need not have been written down in the first quantum like the song on the disc of a phonograph, end quote. However, WMAP results suggest that, in fact, it was. From Lemaitre to Balby, the technology of the grooved record and the shape of an acoustic wave served as apt metaphors for peaks in the cosmic microwave background. Had we some other technology for recording sound in the time of Lemaitre, perhaps astronomers would have characterized these acoustic peaks in other terms. On the other hand, scientists find that acoustic and electromagnetic waves are means by which the universe, the stars, and planets tell their story. Astronomers and cosmologists, since Pythagoras, have never given up on finding music in the cosmos. And now they have. An illustration of our acoustic sun. Oh, it's not too bad. It looks cool. So here is an illustration of our acoustic sun. That looks wild. Very fun. In IndieWare's Project Hail Mary, central alien character uses sound as its primary sensory system versus vision. That's cool. Oh, no, it's an arachnid type creature? Oh no, I hate that. I do not like spiders. Oh no. Oh my. Hey Parzival, how you doing? No worries that you're late. Welcome to the stream. We have a few more pages left, so you can join us for the end of it. Let's see. Precision cosmology. WMAP has not only put us in tune with the cosmos, it has refined and sharpened our view of the extraordinary event that created all matter and energy 13.8 billion years ago. WMAP has taken quantities that were poorly known or only hinted at and turned them into well-measured cosmological parameters. The temperature is measured to a precision of a thousandth of a degree. Since space can be curved according to general relativity, the universe can act as a gigantic lens. To do this vast optics experiment, we look at the microwaves that have been traveling across space for billions of years. The fundamental harmonic of the microwave radiation sets the size of the spot. Radiation from that typical spot size travels through space, and the angular size can be magnified or demagnified, depending on whether space has positive or negative curvature, which is like the universe acting as either a convex or a concave lens. WMAP has shown that the spot size doesn't change, so the universe is behaving like a smooth sheet of glass. The inference is that space is not curved. The universe is flat to a precision of 1%. This is just as expected from inflation. WMAP has measured the mass and energy of the universe with unprecedented precision. The ratio of fundamental to first harmonic powers depends on the baryonic or normal matter content of the universe. Ordinary atoms only make up 4.6% of the universe, to within 0.1%. The strength of the second harmonic is sensitive to dark matter, and shows that dark matter is 23% of the universe, to within 1%. Knowing the mass and energy content of the universe, general relativity can be used to calculate the current age. It's 13.73 billion years, with a precision of 1%, or 120 million years, though that precision depends on assuming that space is exactly flat, which is a good assumption. These numbers have been refined and slightly altered by Planck. The cosmic pie has dark slices and just a sliver of visible stuff. We've also been able to learn about the epoch when the first stars and galaxies formed using the WMAP data. If stars formed soon enough after recombination, they would have ionized the still diffusing gas. That would have recreated the conditions where photons bounce off electrons, as was routinely the case before recombination. This late scattering imprints polarization on the microwave radiation, analogous to sunlight being polarized when it bounces off a water surface. Polarization requires a special direction, and that can only be seen if photons travel freely. That can be only seen if photons travel relatively freely before interacting. Before recombination, no polarization is expected. WMAP saw a polarization indicating that 20% of the photons were scattered by a sparse fog of ionized gas a couple of 100 million years after the Big Bang. This is surprising because astronomers didn't expect the first stars to form that quickly. The sum of all WMAP's improvements leaves little doubt that the universe began with a hot Big Bang. The model is described quite precisely, and any competing idea would have to clear some very high bars of evidence to be viable. It's extraordinary that we can know some attributes of the overall universe better than we know attributes of the Earth. And then I have a figure for you. This is just a simple little pie graph of the breakup of stuff in the universe, essentially. So it says that the observations that we've done of the cosmic microwave background radiation and ground-based observations have determined the content of the universe. So, yeah. So, the normal matter is pretty small. The dark matter is like a quarter, a little less, and the dark energy is a whole lot. So, yeah. All right, let's finish this out. Probing the very early universe. The landscape in cosmology has shifted. Scientists no longer worry about the validity of the Big Bang model. It rests on a sturdy tripod of evidence. One leg is the expansion of the universe, as traced by the recession of galaxies. Another leg is the cosmic abundance of light elements in the first 3 minutes, when the temperature was 10 million degrees. The third is the microwave background radiation. WMAP has advanced the level of diagnostic power of the third piece of evidence to a level that is unprecedented. The Big Bang model has so far passed all tests with flying colors. The frontier of cosmology involves gaining better physical understanding of dark matter and dark energy, and pushing tests of the Big Bang to earlier eras. WMAP has weighed dark matter with better accuracy than ever before, and it has shown that dark energy is an inherent property of spacetime itself, as with Einstein's cosmological constant, rather than being a particle or field existing in spacetime. The current frontier is the epoch of inflation, an incredible trillionth of a second after the Big Bang. Inflation was motivated by the unexpected flatness and smoothness of the universe, plus the lack of space-time glitches surviving to the present day, like monopoles and strings. Inflation got early support from WMAP data showing that the strength of temperature variations was independent of scale. But in current theory, inflation is not one thing. It's an umbrella for a bewildering array of ideas about the infant universe. Since it refers to a time when all forces of nature except gravity were unified, inflation models involve speculation as to the fundamental nature of matter. Superstrings are one such concept for matter, but almost all the theories have to incorporate gravity in some way, so the theory of the very early universe is proximate to the search for a theory of everything. In 2003, the WMAP team announced a new measurement resulting from the polarization measurements and increasingly refined temperature maps. The temperature variations are generally equal in strength on all scales, but as data improved, it became clear they were not exactly equal on all scales. The sense of this deviation was exactly as predicted by the favored inflation models, and different from predictions by rival theories for the early expansion. Exotic, cold Big Bang models were also ruled out. In 2010, using WMAP's 7-year data, the team even managed to use the data to confirm the helium abundance from the Big Bang, and they put constraints on the number of neutrino species and other exotic particles. Most gratifyingly, the data confirmed the fundamental correctness of the model of temperature variations as resulting from acoustic oscillations. The Piper's tune is better understood than ever before. Inflation is required by the data, and cosmologists are honing in on the correct model. Part of the inflation landscape is the fact that the physical universe, all that there is much larger than the visible universe, all we can see. Inflation also motivates the idea of the multiverse, parallel universes with widely different properties that emerge from the quantum substrate that preceded the Big Bang. Our dreams of other worlds should now be expanded to encompass other universes filled with worlds. The ambition and scope of these theories is extraordinary, and it undoubtedly would have amazed Pythagoras to know how far we've taken his idea of a universe based on mathematics and harmony. And that's the end of that chapter. Oh, and right at the end, do we want to become famous? Should we buy followers, primes, and viewers? I don't think so. Let me get rid of that. Bye. But yeah, that's the end of that chapter on WMAP. That was fun. And there was never a good time. But I'm going to show you guys the WMAP map. The WMAP map, you know? Gosh, this is such a big picture. Oh, it's not that bad. Okay. So this is, the whole thing we talked about was that the WMAP mapped the cosmic microwave background radiation to figure out that there are areas in space with like slightly different temperatures. And this is that map, if you haven't seen it before. It's super cool. It's very colorful. And that's it. Ooh. Is something new discovered in the cosmos? I don't know, not today, not by us, but I just learned about some other stuff. Ox Bowman, flat space is, yes, confusing. Yeah, I think Student McLeod, explained it pretty well. But yeah, the curved space-time is more of the effect of an object that has mass, right? So there is curved space-time around things like stars and a little bit planets, I believe, just slightly, and black holes and stuff like that. Neutron stars have more of the effect. But like generally space is not like a sphere or hyperbolic. It's like flat. It's kind of confusing, but yeah. Well, I think that's pretty much it for today. So like I said, that's the last normal chapter in the book, and then we have a little conclusion about which you should be here for. It's next week. Don't leave me. Finish out the book with me. And once we finish that, I am going to schedule us a time. Yeah, it's a solid chapter length. We're gonna schedule a time with Professor Impey to ask him questions about the book, why he wrote it, what the research was like, stuff like that. Maybe I can get him to talk to Holly Henry. Maybe I can get her on too. That'd be really cool to have both of them. Since they wrote it together, I'd like to know about how they wrote it together too. That sounds like a process. But yeah, so I will see you folks here next week if you don't come to the other ones this week. But this week we have astronomy news with hopefully Michael will be back. If he's not back, then we'll see what we do. We'll be here on Wednesday either way. And then amateur astronomy on Friday, and then back with Bookstream Monday. And yeah. Oh, and if you guys didn't know, thank you so much for following. Ziggy's42, welcome to the Teach Astronomy family. I was actually just going to mention, we actually now have over 1,000 followers, which thank you guys so much for, being here all the time and following the channel and helping us grow. It's really exciting to see that, like, back in, when did we start? In like September, we had no followers and we didn't know how Twitch was going to go. And now, not even a year later, we have 1,000 followers and like people that I recognize all the time in the chat. It's like really, really cool. We didn't think this was going to work. And it's great. It's great to have you guys here. And in order to thank you all for helping us grow the channel, we want to do a special 1,000 subscribers, or not that many subscribers, 1,000 followers stream. And we're working on planning it, but we should have a date by like the end of the week. It'll probably be sometime in June, maybe towards the end of June. It's going to be an extra long stream, and we're going to have everybody on at different times. I'm going to be here the whole time because, of course, I am. And we're just going to have a really good time. So, yeah. Ox Bowman, you think you're going to get the book? Yeah, for sure. If you want, if you haven't heard the other sessions and you prefer to, if the book is hard to access or whatever, or if you want to listen to me read it to you, I do post all of these on our YouTube channel. So if you guys want that, let me link it really quick. But it's on the Teach Astronomy channel. And am I not subscribed to the Teach Astronomy channel? That's awkward. But there it is. There's a playlist on there that should work. It's like a Dreams of Other Worlds book read playlist. Or you could just go one by one. I also have Einstein's Monsters on there, which is the book that we read last time. So if you want to watch those, feel free. If not, go for it. Buy that book. I think it's available on like Amazon and stuff. And also you could probably request it from local like bookstores and have them buy it for you, and you buy it from them, sort of thing. But yeah. But I guess that's it. So thank you guys all so much, and I will see you next time. Have a great week.